Good day to you folks. We're talking about perfect squares and square roots today, which I like to call inverses of one another, and I may not be technically correct in that, but they're kind of related in a way, just like multiplication and division are related, and just like addition and subtraction are related. When we talk about perfect squares, we find perfect squares by multiplying a number times itself. For instance, 6 times 6, or 7 times 7, or 20 times 20. And the number that is the result, the product of that, is what we call a perfect square. So there's a little bit of multiplication work that is involved in this, and it might be difficult and it might be quite easy. When we try to find a square root of a number, we're starting with a relatively large number, and we're trying to find what number times itself equals that value. And there's an example here. It says the square root of 100. The notation for that is what looks like a division symbol, division box symbol with a little hook on it. I like to think of it as like a check mark and then a line across. The square root of 100 is 10 because 10 times 10 equals 100. And just to give it a quick read, a square root is found by finding a number that, when multiplied by itself, yields the given number. So it's kind of the opposite of this. These are kind of opposites to one another. That's why I call them inverses. How are they similar? Well, they're similar because they both involve multiplication in some way. Either by checking the work or by actually finding the answer, we can use multiplication to facilitate that. We also usually use only whole numbers. Now, that's not to say that that's always the case, because I could tell you that the square root of 2 is 1.414, and I think it goes a little further too. So we don't always have to use whole numbers for this, although most of the time when we deal with them in the middle grades, we're dealing with whole number values. I think it's important to see decimal values in this because it kind of gives them an appreciation to the whole numbers. I encourage you to take a look at this and copy down what is relevant to you. This is a Venn diagram. We're showing the differences and then we're showing the similarities here. So take a second to pause and write if you need to, as we're going to move on in 3, 2, 1. Moving on. I am not going to drop the board on my head. I'm getting good at this. All right, by the end of the year, I'm going to be fantastic. So I want to ask you a couple questions. I want to ask you, is there a pattern in perfect squares? Or can we call square numbers a pattern if we write them out? I think we can. And these are just a few of the examples here of some square numbers: 1, 4, 9, 16, 25, 36, and they keep going on, evidenced by the 3 dots. When I go from 1 to 4, if I just thought about this as just a simple number pattern, what can I do to get from 1 to 4? Well, I'm increasing, so I can say that I'm increasing by 3. I guess I can say that I'm multiplying by 4 as well, but that wouldn't actually work if I were to go here. I can't multiply by 4 to get to 9. However, I can increase, and I can keep increasing, and I encourage you to try that. So what am I doing from 4 to 9? What am I doing from 9 to 16? What am I doing from 16 to 25? And 25 to 36. Do you notice anything about the numbers that I've written here? What you might notice is that each of these are odd numbers, and they are in order. They follow each other. And since I can say that these are consecutive odd numbers. If they're consecutive odd numbers, then there's an increase from this to this of 2. Can't really see that. Sorry about that. I'm increasing by 2 here. I'm increasing by 2 here. I'm increasing by 2 here. So I know that this looks kind of busy, but I want to say to you that there's actually what I guess we could say there's a pattern in a pattern. In this pattern, you see an increase of 3, 5, 7, 9, and it's kind of growing every time. But in that pattern, you should also see that this is increasing by 2 each time because they're consecutive odd numbers. I'd like you to follow this out all the way to 400. I'd like you to write out all of your square numbers, and if you have to calculate them, so be it. But calculate all your numbers to 400, and then I want you also to find out how this pattern actually works its way out. If you can show that to me in class, I will give you 5 points in your next classwork assignment. I want to see how many people are watching this video and see if the rumor gets around. So hopefully it does. What about cube numbers? I wonder if cube numbers can do the same thing. Now, I gave you only a few numbers because I want you to actually figure this out yourself. A cube number is a number times itself, just like a square number is a number times itself. So cube numbers, remember there are 3 numbers here. There are 2 numbers to multiply here. Now, I give you the easy one. 1 times 1 times 1 is just 1. So sorry, I'm going to give you the easy ones. But I gave you also 3 times 3 times 3 is 27. Because 3 times 3 is 9, and 9 times 3 is 27. I didn't give you 2 times 2 times 2. I'll let you figure that out, and that one's pretty easy. What I want you to do is I want you to follow this out. Keep going a few extra steps, and I want to see if you can make that connection. Can you do it? Show me in class. Prove it to me. Convince me that you know what you're talking about. Convince me that you saw this. And have a good day.